Hello, this is Lab 5, Faraday's Law, which is for Physics 2212. The main goal of this lab was to measure the time it took for a magnet to fall through an aluminum tube. The amount of time was measured experimentally and computationally. The two values are also compared in this lab. The big physics idea that is occurring in this lab is that a magnet is falling through a non-ferrous tube, which induces a current, creating a field. This field then acts back on the magnet, opposing gravity, which causes it to fall slower. Here, Faraday's law is used to determine the change in the magnetic flux, allowing us to determine the current in each ring of the tube. The Biot-Savart law is used to determine the force the falling magnet has on the tube. The experimental version of this lab resulted in the magnet spending 1.544 seconds in the tube, while the modeled version resulted in the magnet spending 4.053 seconds in the tube. Theoretically, the modeled version should have resulted in a shorter time, but reasons for this discrepancy will be discussed later. To determine the experimental time the magnet spent in the tube, 5 trials were conducted. From these 5 trials, we could tell that the magnet spent an average time of 1.544 seconds in the tube. Questions and observations from the experimental portion of this lab. Why can't a ferrous tube be used for this experiment? Well, ferrous tubes are magnetic, so the magnet would be attracted to the sides of the tube and wouldn't freely fall through the tube. Some observations. Well, it took the magnet noticeably more time to fall through the tube than it would have if we would have just dropped it while it wasn't surrounded in the tube. This means there was another force acting on the magnet, which we'll discuss later. I also noticed that the magnet would occasionally hit the edge of the tube, causing friction. This will cause the magnet to spend more time in the tube because of this extra force acting on it. This is a computational model of what is occurring in the experiment. As you can see, there is a red and blue current above and below the magnet. What does this mean? Well, when the increasing change in flux is downward, the induced current is moving counterclockwise. This is being shown by the blue current while the red current is moving clockwise. This is the code used to create that model, and the main thing I want to discuss here is the magnetic moment used. This moment was calculated in an earlier lab and is much bigger than the actual value. This large magnetic moment will cause the simulation to show that the magnet will take longer time to reach the bottom of the tube. Here's the rest of the code that was used to create the model. This is a velocity versus time graph for the magnet. From this, we can see that while in the tube, the magnet pretty much had a constant velocity. The total time it took for the magnet to fall through the tube was 4.053 seconds. This is much longer than the 1.544 seconds that was experimentally determined. This is odd because we would expect the experimental value to be larger because it wouldn't be experiencing friction like in the experimental version. The reason for this is because of the magnetic moment used. Like I said, the actual magnetic moment of the magnet is smaller than what was calculated in an earlier lab. This difference caused the model to show the magnet spending more time in the tube. If the magnetic moment were to decrease, this time inside the tube would decrease. So what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Well, the induced current would become larger. This larger current would result in the magnet taking more time to fall through the tube. And what if the holes and slots were cut into the tube? How would this affect the ring currents in your model? Well, the induced current would decrease here and cause the magnet to spend less time in the tube and basically fall faster. This has been my Lab 5 for Physics 2212. Thank you.